Great. Good morning, everyone. Thank you for joining the ARMA Technical Committee on Induced Seismicity's monthly webinar series. This week, or this month, we have chosen the topic of geothermal energy to discuss potential issues that may arise during its development, specifically uncontrolled seismicity. And so to discuss the topic, we have assembled an outstanding panel, and they include John Schmittbuhl, Stefan Wiemer, Ernie Majer, and I'm sorry if I mispronounce any names, as well as Trenton, Cladouhos, and they will take a few moments to introduce themselves and briefly discuss the type of issues they're going to focus on. And then once we're done with that, we can pose some questions from the moderator, being myself, and we'll proceed to the audience to share their questions and get feedback from the speakers. So with that, we're going to start with John Schmittbuhl. This is the order. Then we'll go to Stefan, to Ernie Majer, and then eventually to Trenton once he succeeds to join.
Okay, so good morning, everybody. Thanks for the invitation to participate to this this webinar. It's a very interesting topic for me. And just to introduce myself, so I'm working in France at CNRS as a research scientist. I'm a geophysicist, somewhere between seismology and geomechanics, working at University of Strasbourg, so on the east of France. And I'm leading the local interdisciplinary program about geosciences for the energy system transition. That is quite rich because it includes a few colleagues from social sciences and also from the engineering departments, together with the geoscience department. So next slide. I've been involved in several regional deep geothermal energy projects in the Rhine-Graben. So from the map, you can see that it's really the east part of France, and you have a zoom on this this area, the figure, where it's a description of the different projects around the city of Strasbourg and to the north of Strasbourg. And the green figures or symbols correspond to ongoing project for deep geothermal energy. And you might see the one around Strasbourg and also the more historical one to the north, Sulzufore and also Rittershofen. And the blue dots, the blue stars are the future projects. And I will just comment very quickly about that. There is a general trend that history started around the Sulzufore area, where it used to be a very old history of subsurface exploitation because of the oil feed of Pechelbronn and knowledge of the subsurface there, coming from very long, 200 years of history. And it's very important for the uptake from the population because they are used to this type of exploitation. And this is a significant contrast with the more recent project to the city of Strasbourg in an urban context, where recently there was some development that has been stopped from a recent accident, the Vandenheim project that stopped, and I will make just a short overview of that in the next slide. Sorry, I'm not just finished with the. Can you go back? I just want to say one more word about the future of this technology, because of this accident initiate a very important controversy on the EGS technology and some moratorium of the project in the Strasbourg area. And as you can see from the figure, the new project or the ongoing project are far from the city in the north, to the north. And this is for a new strategy, which is shown here. It's for the cogeneration of lithium and heat. And this is the new trend for the future of that technology in this area. Okay, so next slide. A few words about the lessons from the the failure of the Mandanine project 2 years ago. So this is in one slide a summary of this project and the problem attached to that. So the Google map is a zoom on around the city of Strasbourg, which is at the center of the image. And with colors, you do see the induced seismicity. The blue one is with some pink lines. So that's the trace of the wells at depths, so significantly deviated wells at 4 kilometer depth. And the blue seismicity is the really induced seismicity because of the work at the well. And the stars are the large induced event to the northern wells that was up to magnitude, local magnitude 3.9 and stopped the project. But actually, there are still very important questions to solve and to understand for this type of project, which are sketched on the figure, which is the history of the seismicity. Is that the red one is the red cluster of seismicity, which is 5 kilometers apart. So how could be such a remote triggering of seismicity 5 kilometers apart? And second is that the biggest earthquake that I mentioned happened 6 months after shutting. Yeah? So it's about understanding the long delay in this type of project, which are, I think, two important scientific questions that are still quite open in this problem. But the main lesson I would like to emphasize for this the sort of accident is that the expertise is to say that it was lacking for a careful exploration phase and a careful analysis of the stability of the existing natural faults, which were targeted in this system. Okay, so to illustrate that, next slide. I would like to just to go back a little bit to the concept, because we are at a point of possibly having a bifurcation in the development of this technology. I think the concept is, at least in the land graben, it used to be the upper graph, the 3D block, where you do see what I try to sketch as a really enhanced geothermal system, in the sense that the project tried to address existing natural objects like natural faults, natural fluid, a very important component, the access to the natural fluid, which is actually the resource. So it is trying to target this existing fluid and how to extract it and how to recycle it. So this is the technology that is ongoing in the right graben, but there is another one that is a sort of reaction or possibly a perspective for another approach, which is the bottom sketch, where the project tried to go away from faults, away from sort of natural complexity, and try to develop the heat exchanger typically from a multi-stage technique, far from any faults, where it is sometimes difficult, and not sometimes, but always difficult, to separate the hydraulic properties of the natural fault from their seismic properties. So to avoid this new route is going away and trying to develop a new type of reservoir. We are not along this line in the right graben, but of course there are some perspective for that. The American project Forge is a very good example of that, and it might develop in Switzerland, so close by the right graben in a close future at Haute-Saône. And to finish this very short introduction, next slide. I just want to point out that in terms of perspective, at least at the French scale, at the national scale in France, we are building a long-term project for developing the technology and I just want to give three words about the perspective, saying that there is a need for deep wells, scientific well for understanding the structure at great depths in such a basin, because it's obviously not so well understood. It was supposed, for instance, for the Vandenheim project, that it was possible to translate the known and successful projects of Sulzufore and Rittershofen to the city of Strasbourg, where the graben is much deeper, and that was not so trivial. So a better knowledge at depths of the transition between the basement and the sediment. So this is an important development. The second one is, in this technology, the target is the fluid. So we realize that we know a lot about the rock, the solid part of the reservoir, but little about the fluid part, and a deeper understanding of the fluid circulation at depths is necessary. And the third part, the third perspective, is really to change the concept for the acceptability strategy, and to go to a much stronger involvement of the population, and shift to what our social science call research, responsible research and innovation, where there is a strong engagement of the public. And for this, we have a starting point, which is what we call citizen seismology, where we try to deploy instruments within the citizen houses, and have their involvement in and share the monitoring of the project, and have their some of the involvement from this. Okay, so that was a short introduction, and I'm of course open for any question when it will be time for discussion.
Thank you very much. And so this idea of transition or bifurcation, is also taking place in the U.S., and I'm sure maybe Trenton will mention that in his presentation. Are you ready, Trenton?
Yeah. Yes, I'm ready. Okay. You see my screen?
Yes.
Okay. Oh wait, now I can't see. Is this, you can see my mouse here and everything?
No, you can share again.
Oh, okay. You were...
So do a stop share and then reshare. Yeah. That green.
There we go. Can I do it?
Yes.
Okay. I've been involved with induced seismicity projects since about 2008 with the geysers, and I'm not going to talk about that at all today, but that was really right after Basel, and the project really had some serious problems dealing with the public perception of induced seismicity. So that was my introduction to it, and it wasn't necessarily a happy one. After that, I worked on the Newberry volcano EGS demonstration, which is what I'll talk about mostly here. And now I'm back to working on that. And then I will talk about induced seismicity results at Blue Mountain, Nevada, which is the Fervo Project Red result that they published. And my affiliation has been at when I was at Newberry and Geysers, it was Alta Rock. Currently, I have Stoneway Geothermal is my own consulting company, and Mazama Energy is the new company we're creating to continue work at Newberry. And I guess my overall point is just, I think we've made, with the reference frame of the geysers in 2008, I think we've made really great progress in how we do induce seismicity mitigation and planning. So back in 2011, the process or the planning we did is at that time, the induced seismicity mitigation protocol was under development in the U.S. And Ernie Majer, I'm sure we'll talk a little bit about that protocol. We did created a decision tree for triggers and mitigation actions. It was, eventually that became known as the traffic light system, and I think that was at the time starting to be used, but now it's completely moved over to that. Just looking back at it, I was surprised we didn't call it a traffic light system at the time. And but it did have pretty much the same sorts of guidance as a traffic light system. We did have a special portion of ours which is we couldn't go into the national monument, our seismicity, so we had to also not just have triggers for size, but also triggers for locations of earthquakes, which would be common in areas with any sort of sensitive structures nearby. Our shape map was based on the largest postulated event of a 3.5, used a generic ground motion model, which I think got it way off. It predicted a maximum acceleration of 0.2 gravity within the main area around the well, which I think is much too high. So I'll show you an update of that later on, but I think the ground motion model wasn't very good at the time. And then we installed, I think, what was a very good microseismic array of 15 stations around the well, including a strong motion sensor. In 2014, after the first stimulation, we made some updates to our induced seismicity modeling or our monitoring. At that time, we started doing real-time tracking of moment versus injected volume. And that was based on some work that Art Majer had done in the meantime, basically correlating, or I should say he updated, correlating maximum magnitude earthquake to injected volume. This process has been, further updated since then, but this is something we adopted in 2014. Also tracking the B value through time. Again, that's something that's become more common. And then just to show our final seismic catalog, we had a complete detection down to magnitude 0, and our biggest event was of 2.4, which only caused a shaking of 0.000001 G at the strong motion sensor. Now we've come back to Newberry, and I think obviously if you use the same site, you're going to keep learning more and more about that site, and you'll be reducing risk all the time. So really, this is the third stimulation at Newberry. We're going to be doing it at super hot temperatures now. So we've introduced a new variable, which is will near ductile rock or just at least hotter rock reduce seismic risk. It's certainly been proposed. I think it's a theory at this point that we need to continue to look at in the field and lab. But now that we have better data, we can use the focal mechanisms from the past simulations to look at actual slip tendency with better data inputs for the probabilistic seismic hazard analysis, which we redid recently, working with Ivan Wong at Lettuce Consultants. And now we have a better shape map that is now calibrated to real site response model of that magnitude 2.4 we saw, but other data as well. Alterock Energy owned Blue Mountain when Fervo first started looking for a site to work on, and so I've been involved with their work kind of from the beginning, and I think it is a great model for how to do an induced seismicity mitigation plan and monitoring, but also it's also this new model of doing fracking, we'll call it hydraulic fracturing. Rather than in impermeable rocks, rather than trying to find permeable features that need to be enhanced. They installed 9 broadband sensors, 2 strong motion sensors for IS&P. They ran that for a total of 3 years elapsed, but 2 years of data during a proof of concept, an injection well, simulation of the injection well, stimulation of the production well, and then most recently flow testing. And during that entire period, and they injected a lot of fluid, enough for 102 fractures. The largest event they saw was under magnitude 2, so they never even hit their yellow light. And that's because I think that is largely because they're outside of an area with faults and fractures. And they also use distributed acoustic sensing in 3 wells. The blue is the injection stimulation, the red is the production stimulation. And what you see up here is where the natural geothermal field is that's been operating for 10 years. You see a lot of that seismicity is there, and not really as much if you look at the area that they were doing the tensile fracturing. So this is kind of a hybrid type of response. And all these figures are from Norbeck and Latimer on Earth Archive if you're interested in seeing more. Thank you.
Thank you, Trenton. So next, Stefan Wiemer.
Are you seeing my screen then? I
Yes.
hope. So thanks for this opportunity. It's exciting to be here. I'll try to be quick. I'm professor of seismology here at ETH Zurich. I'll direct the Swiss Seismological Service and been involved in induced seismicity for quite some time. And I'm always envious to see how other nations are able to make good progress, partially because our challenge here in Switzerland is that actually doing deep geothermal energy in Switzerland is pretty hard. We had the Basel failure, St. Gallen, which was more hydrothermal, was a failure. Pohang had back implications, so did Strasbourg, actually, as Sean knows. And we are right now, we being in this case, not us, but the GeoEnergy Swiss trying to put the Ozone project forward. There's been a long ongoing thing, but you see this picture here of people that are really upset about it and also saying that fracking, which of course EGS is not per se fracking in the strict sense, is something they're not really looking forward to. So it is very difficult to make this work in areas of relatively high population density with a population that can turn quite negative. So how do we make progress is something that I'd like to show in just 3 slides here and from our perspective. One thing we as ETH, but also industry tries to do is to understand better the seismicity, how it evolves and how multi-stage stimulation go. So we have this Pedretro Underground Laboratory for Geoscience and Geoenergy where we build a scaled experiment of multi-stage stimulations at a 1 to 10 kind of scale in order to really have this stimulations understood and the way to limit seismicity and so on and so forth. You're welcome to look at the website of that. What else can we do to regain the trust of the people? I think we can try to be smarter. And of course, that's been shown before. The better we are able to have our risks being managed, the better are we able to then also forecast how seismicity works. So being smarter means we have classical traffic light, but we extend then increasingly to have what we might call the adaptive traffic lights. And there's a workflow here that don't stop at just forecasting rates, but really go to hazard and possibly to risk, and then have smarter decision modules. There are data-driven approaches that allow you to do some real-time mitigation of risk. And there's also machine learning that can increasingly help you to deal with all the data that you're collecting increasingly. So being smarter, I think, is an important part of tackling this challenge. And the last one is really to, how do we regain trust? I think learning in safe places is an important lesson, because the more we can do this in areas where there is really very little risk for whatever reason, one of them could be like in the Forge area here, there are very few people, then we are able to build up really these very detailed models. And I'll just show the waveform propagation that we have been put forward for the Forge site for an induced event or so, to understand things and learn at a full-scale reservoir without having to risk of upsetting people. And once we are well aware, then it should be easier to convince people in other places as well that this technology is ready for deployment. Thank you very much.
Thank you. Excellent. Ernie, are you ready?
Ernie, you're muted, but I can show your slides too if you'd like. I have them up.
Okay, go ahead.
Okay.
I don't know if you got my most recent edit. Okay, I just want to talk about 2 recent things we're doing. Now, it's kind of ironic that we're having it this month. This is the 50th anniversary of us getting into DOE. And it wasn't DOE then, it was the Atomic Energy Commission. And I was out in Nevada as a student putting in smoke paper recorders. But we've progressed quite a ways on instrumentation. And we've also progressed towards even having something called the best practices. We started that out in 2004 as part of the EIA Geothermal Annex. Stefan was on that with me. And in 2004, there was a protocol, and then in 2008, there was another one, and then DOE, United States, decided they wanted their own. And so in 2012, we had our own protocol and then no best practices. And now we're updating it again. It hasn't been really updated since 2012. What comes out of a best practice is something called an induced seismicity mitigation plan. What do you do in all steps of implementing it? And as Stefan pointed out, dealing with the public is one of the main reasons for best practice in an ISMP. So we're streamlining it, make it more readable. It was a little wieldy. I don't know if anybody in the world had even read the whole thing. And so we want to make it a little more readable. And it's meant for stakeholders. And the data are coming from stakeholders, mainly the people who are affected by induced seismicity. And that's being the public as well as the contractors. It's guidelines, not regulations. It's risk-based. And it's a living document. And then also I want to talk about is a new project, well, not very new, a couple of years old. DOE has something called the PRIZE project that is next generation of high temperature sensors. I've always felt, I'm an instrumentation guy and I'm a data guy. So I've always felt that we need better data. And so that's what I'll talk about. So next slide, please. And so there's a lot of things to consider when you're doing the MAQ analysis, even what I call the basic things, the magnitude, location, source mechanisms, volume change, and things like that. And also what I think is being ignored now is people go out and do a lot of monitoring with quite sometimes very deep resources, but maybe for a year or two, and then people ignore it. What about the long term? The geysers is long term. I think they are a model of what they started out in 1960 and started seismicity, of course. And they did not want to even admit that it was due to them injecting water into the ground and producing water, steam out of the ground. But they've been a completely 180 since Calpine took them over. And I think they are the model of how to deal with the public and how to deal with induced seismicity at both the public level and then also by actually manipulating the injection places, injection rates, all those things. And therefore, but I always felt that we need better data. So what data are needed? Let's go to the next slide. So this new DOE program is part of something called the PRIZE. I don't know if you're whole, but it's thinking out of the box using non-traditional, not the oil company type sensor people, although they are interested in it, with these characteristics. And John was just talking about going deep and getting better imaging. And I think that's crucial. There are sensors that do this, but they're not high temperature. And so they say, well, why don't you just use the ones they've been using in the nuclear industry for very high temperature monitoring. Well, that's fine if you're only standing 100 yards away from where you are, but 300 meters or more, you have a lot of issues associated with in situ conditions, caustic conditions, things of that nature, getting the signals up without attenuation. I mean, fiber is beginning to advance that, but that's true, that doesn't have true 3C sensitivity. You know, you can't get the full vector field, which I think is important to actually get down in there and see what's going on. The oil companies have done that in some of with fiber, and this was with traditional sensors, but again, not at 225 or 250 C for any amounts of time. So hopefully, and what we're seeing some real innovative things coming from parts of the industry, the aerospace industry, things of that nature, that hold some promise. Now it's not, and that number 9 and 10 down there, cost effective and easy to rapidly deploy in a caustic environment is not going to be easy. So anyway, I can talk more about that if people have questions in it, but we're pretty excited about this program. And I think for the first time, we'll really get close down right there where the action is going on to look at all these things called dry events, is it poroelastic effects, you name it, all these different effects that cause seismicity. What really are those micro earthquakes telling us, Anyway, so that's what I hope to, maybe if anybody has questions on how that program is or where we are in our best practices. We hope to finish up the best practices here in the next several months.
Great, thank you very much, Ernie.
Yeah.
And yeah, so data obviously a critical component of mitigating risks, and so as is characterization, right? So that's what Jean was talking about: site selection, characterization, and monitoring, and all of that hinges on data. So it's great to see that there are significant efforts being put on resolving that challenge. Now let's start with Jean. So you mentioned this bifurcation from the shear stimulation or possibly near fault resource development, possibly to the multi-stage fracturing, and Trenton also indicated that in the case of Furwo. Now, is that viable really, or how will that maybe contribute to mitigating the risk? It would seem to me that we still have to kind of bear in mind that there could be hidden structures, as we have seen in the oil and gas industry, that can become reactivated during hydraulic fracturing. So what are your thoughts on that?
Yeah, it's a very vast question, I think. And it's related to one of the question in the chat, is the kind of objective of those projects. Do we want to exploit the existing fluid? I think is, at least in the Rhine Graben, is a key parameter or a key objective. So then the main objective becomes to identify this fluid at depth and to go and get it. Yeah. And that's one part. And also when you have it at the surface, it's a kind of a material where you can mine the heat or mine the minerals that are into it, like the lithium, and there is a very strong development of that and this cogeneration. So this vision that it's a mining process, extracting from the fluid, kind of fluid ore, and then a question of re-injecting it into the formation somewhere without impacting your production domain. So this vision about mining fluid is used to be the objective in the Rhine Graben, and to have EGS oriented to that. So if this is the objective, there is basically no choice. I think a multi-stage technique where you start from a quasi-dry system is not going to be suited. So I think this is, to answer the question in the chat, this is why France is kind of keeping on this objective of exploiting this fluid. And possibly there is still some perspective that the extraction for the lithium is becoming more beneficial than the heat itself. So I think this is still very open. And I'm not really in the business to really answer precisely, but this is to say that one case is, to me, dedicated to the fluid extraction. The other one is more in question of heat production. And of course, this new multi-stage strategy is possibly very interesting. A limitation we have in France, and that's what Stefan mentioned, is the fracking perception. And it's very much depend on oil technology, oil and gas technology, that for instance, in France, are defined as against the law now. Strictly speaking, it's a lot of question about defining it precisely to know how much it will differ or be similar to oil and gas practice, but this is not so easy. But this is to say that this strategy for the moment, at least in France, is not possible. And it's interesting to see that Switzerland is basically accepting that and pushing that technology instead of going back to a sort of fault strategy. So that's interesting. Another one, just as a comment, is that this fault strategy, if we can call it this way, has been extremely successful in Alsace, in the Rheingraben through the Rittersofen project. And this project has been successful for now almost 7 years, and so there are possibility of success. It's not just a matter of failure. And some problems is to, I mean, some issue is to define why this one has been successful and why the other are not successful. So one of the question is the depth. Is it a depth issue? I'm not sure it is a depth issue personally, but I don't want to go to this debate. I think what is very important in this type of project is to have to put a lot of effort on the exploration, because it's going to be the slightest modification of the natural system, and which require to have the best knowledge of it. And this is where the effort has to be. So this is a strategy. So then put a lot of effort on the exploration, but this could be very costly, and the balance is not always easy to get. Yeah.
Any thoughts from the other panelists on this issue and the related topics to it, in particular public perception of hydraulic fracturing?
I'll take a little bit on that, not so much the public. Oh, sorry, Stefan's got his hand up, but
No, you can go first. That's fine. Go.
Okay. So I think that you know, avoiding the pre-existing features like Fervo did or Forge has done is definitely one option. I think it is a bifurcation, though. I don't think we're going to get away from the idea of targeting pre-existing features. And I think one thing is all existing geothermal fields are in pre-existing features, and then we have induced seismicity issues in existing geothermal fields. And I think, you know, like the geysers, the best practices for induced seismicity are still important. So I think we still have that, and I think there's going to be a lot of edge cases where you do a hydraulic fracturing type thing at the margin of existing geothermal field, because that's where the heat is, and you're going to always want to drill shallower rather than deeper. So I think it's not really a binary that it's you know, if we can get away from induced seismicity issues if we, you know, change the strategy here and do more fracking.
And it would seem that, and it would seem that we really need induced seismicity to some extent anyway for reservoir characterization, right?
Right. Yeah.
So Stefan, were you saying something?
Yeah, I was going to say two things. The first one is there are people that have arguably said that these multi-stage simulations are significantly less seismic risky than these more massive scale fracture-oriented ones. But John has indicated, yes, in some cases it works perfectly fine, in others it may not. But going closer to bigger faults is always a slightly tricky one. So I have some sympathy for people like Peter Majer that says the multi-stage is the right way to go, because then you can avoid the falls and have that controllability. Overall, I think that has its benefits in the system. Yeah, I'll stop here.
So a couple of other questions that kind of come through the discussion that you guys presented. One is this idea of adaptive control, monitoring and taking measures to lower the risk. And of course, AI and machine learning, you mentioned that, Stefan, and of course, at more advanced data acquisition systems that Ernie Majer indicated. Can you elaborate a little bit, both of you, on these particular aspects? That is both the data acquisition as well as the role of AI and machine learning, and And how far are we from I guess if you want to call it the holy grail of real-time processing and changing the injection procedures?
If I may start, Ernie, I guess we're actually getting pretty close. And a bad example was Pohang in 2017, because if you look at the reports, they had relatively little situation awareness at the time, a minimal level, and many other projects do much better. And I think it's clear that if you don't have a good awareness of what is happening, your reaction time will always be slower. You don't have the insights or so to take actions. If that's good enough, who knows, but I think it should be done. And there I do see a lot of potential in all the machine learning methods that are available to do real-time locations. Now, many projects did quite well with real-time processes anyhow, but we can go further. Where I usually tend to think it's the hardest part is to really then have online real-time reservoir models connected to the seismicity, these being adaptively updated. That's a taller order, because these reservoir models are often a bit hefty. You have to calibrate them on the fly. You have changes and so on. You have uncertainties in your catalog parameters. The next forge stimulation in February, March will go beyond what people have done. And I think we're hoping that there we can demonstrate from our end and some others how well this is by now possible to really do a real-time reservoir characterization based on the online real-time seismicity that we observe.
Great, thanks. Ernie? You're muted.
I agree. There we go. Now, I agree with Stefan. I mean, we have real-time detection now and things of that nature, but it's the real-time processing of the data and coupling it to the reservoir models. I agree with Stefan. I mean, and Forge does offer the opportunity. There are other things that have been done at smaller scales, that Stefan mentioned that, but Dreidel, and then also we were doing that sort of stuff. I don't know, up at the URL in Canada a long time ago to look at scaling effects. Do we get the same effects at -5 events versus the -1 events in a geothermal? So, but yeah, I think Stefan is right. I agree 100% with him, and hopefully we're trying to get the data to do that. The better. What I always say, we're not. If we'd love to sit in the front row of the orchestra, but we're out in their lobby right now, listening, and we miss a lot. So the better we can get definition of events, and we'll understand the reservoir creation success, as well as mitigation, and saying, okay, we better back off now, guys, or do something else. So the geysers, they do that. They actually move their injections around as they watch the seismicity evolve throughout the field. And that's a big field. They have 500 wells up there. They're not all active now, but that's how many wells they've drilled up there. So,
yeah, thanks a lot. And we do have a number of questions in the chat, and yes, maybe you and Matty can begin to pose those to the panel.
Sure. Yes, I think Matti, go ahead.
Sure. The first question is from Jeremy Bulk. He was wondering if the slides of this talk will be shared. So Jeremy, usually we share the recording in the YouTube channel that we have made for this webinar series, but the slides, there is no promise for that. You can reach out to the presenters and get the permission to receive them directly from them. And the other question is from Eric Willeprox. So the question is, I was under the impression that discharging back colder formation fluid in the hot formation, for example, Vendenheim, could have triggered seismicity by changing the formation stresses. Is this cause sustainable? I think this is the question from Jean.
Yeah, I can say something. I try to answer this. So this is
Sean,
about
sorry to interrupt, but we could add that to that question. Another one that is probably also to you by Yason Grigoratos, who is asking whether France doesn't tend to keep targeting deep pre-existing fault structures, despite what happened in 2021. So sorry to interrupt, but there's sort of two questions.
Yeah. I addressed a little bit the second one in my previous comment, but I can say a few more words. So the origin of the seismicity at Vandenheim, of course, is under expertise. But the first phase of this expertise came out that the two main reason or origin is related to the following things. First, as I mentioned it, the knowledge and the stability analysis of the existing fault was not sufficient, because it was at least one direction of faults that were Hercynian faults, so very old inherited fault orientation, who was responsible for all the largest events. And this is when injection happened in those structures that they induced a significant seismicity. Those structures under the in situ stress field were very close to instability, and they reacted very strongly to the injection. So it's about lessons is about careful stress measurements for those projects and careful exploration in terms of good knowledge of the fault orientations in the project. So this is back to my comment that exploration is a very important part in this type of project. And second is the volume of fluid that was injected. And I think Trenton showed the graph where there are kind of classical statistics about the link between volumes, injected volumes, and typical magnitudes of largest events. And according to the injected volume in Strasbourg at the Vandenheim case, it is clear that it was a very high risk to go over the magnitude for the red light of the traffic light system, which was magnitude 2. So the volume were not compatible with this level of the traffic light system. Yeah. So it's other reason, but that's the two main, the two main ones. And related to sort of a second question that is a follow-up of that one, why France is continuing on that strategy to target fault. I think for the moment it's a lot of debate first, and this is there is a moratorium in the Strasbourg area and questioning a lot about the technology somehow. But as I developed lengthily, I think maybe too lengthily, is that here the objective is to get the fluid, the natural fluid that is, it's a trapped fluid in the Rhine Graben, very energetic and rich in terms of minerals. And this is the resource that is targeted. And to go with faults is maybe an important strategy for that. So I think this is why such a strategy is for the moment kept, with the complementary argument that to go for multi-stage, it's getting close to fracking, and we have some very strong restriction by law in France about that.
Great. So the other question is from Jeremy. He's asking, in Oklahoma, over a much larger area with optimally oriented faults being a strike slip with little vertical offset, and commonly in the basement, a remarkable fraction of induced earthquakes occurred kilometers away from any mapped fault. Is this a problem for more compact geothermal projects? This can be a question from Trenton or Ernie.
I feel like, Madi, we may as well open this one up to the whole panel, I think, because all of them probably have things they could say on this point.
Yeah, there's a related question, that is, what is the hypothesis for mechanisms of delayed seismicity, the one that occurred 6 months after shutting or something? Go ahead.
Well, I'll let someone else on that hypothesis, because I don't really have gotten an update on that. But I would say that hidden faults, or I mean, geology is complicated always, right? And so I think the best way to find faults in the basement is to start injecting fluid into the basement. So unfortunately, so that is, you know, we can do a lot to try to characterize these the geology, but you know, if it strikes at faults with no offsets and you know, ancient faults with stored stress on them, it's going to be really difficult to eliminate those. That's why the monitoring is so important. And you know, once you might see some sort of planar feature that you didn't know start to light up, you may need to change your strategy. I think the geothermal industry is held to a much different standard too than the oil and gas industry as far as induced seismicity. That's kind of the lesson of Oklahoma and Texas, I would say. So, but I think geothermal's got to be at that higher standard.
Jeremy, is there any, was the Pawnee earthquake on an unmapped fault? The 5.8 Pawnee earthquake?
I can't, that's hard to tell. There were suggestions that it was on a map fault or that it was on the intersection of a couple of map faults, but the interesting case was the Fairview earthquake out in western Oklahoma, where the whole cluster of earthquakes showed us where the extension of a fault that one of the companies had given us, but it, you know, it ran to the end of their seismic line and stopped there. All the earthquakes occurred in a very solid straight line directly to the northeast of that northeast trending fault, and showed us where the fault really was.
Yeah.
Yeah, the Rocky Mountain Arsenal waste disposal project was that in the 70s? You know, kind of showed us that very early on.
Yeah, and I think if you look at normal hazard assessment in California, what's the number? They guess that they miss at least 50% and more of the magnitude 6 or 6.5 falls or so. So we really don't know where faults are in the first place, and even geophysical mapping can only be really relatively limited in realizing where they are in bedrock specifically. So I guess we have to really acknowledge that limitation.
Yeah. The
geothermal industry live with it, and it's
public service for everybody.
If we pretend that we know all faults and nothing can happen because there is no fault, we'll are likely to then disappoint again because there will be other faults popping up. So it should be the assumption that there may be faults we don't know about, I guess, while we still try to look for the ones we can find. So
yeah, and then we come back around to the adaptive mitigation techniques. Is do we have the techniques to really mitigate when we do find the faults inadvertently?
Yeah, and fortunately, seismicity mostly starts small, and the big ones come a bit later after you have had some seismicity. So that is different from natural, where, well, your background is so, but you have a better chance of identifying a ramp up of seismicity and then stop or do something before it gets too big. So that's an opportunity. I was going to take a stab at the hypothesis question. Mechanisms or so. And just saying one thing, I mean, in Basel, there was an injection in 2006. In 2000, I don't remember, 14, 15, they decided to then close the well finally and say, now let's get rid of this water that keeps gushing out. And shortly after, seismicity started to pick up again, not going up to big earthquakes, but we went up to almost a magnitude 2 again. So what that says is that once you have changed the pressure condition, especially in this relatively tight 5 kilometer deep granitic rock layer or so, you have really a very critically stressed fault cell that react to very tiny changes in pressure, because the closing of the lid was a very tiny thing that was happening then further away in the reservoir. So once we have perturbed the stress condition, it does take in some environments a very long time to come back to the natural background state. And therefore is one reason why you have these long decay rays.
Any other comments on that?
So the other question is from Andres Chavaria. He is asking, at Fairview, we ran seismicity and strain monitoring with fiber DAS. Is a strain something that is being considered elsewhere? I would like to add other monitoring techniques, surface tilt meter or DSS or DTS, other methods that can be used during geothermal site monitoring.
Yes, that's being considered now. The desk out at Ford's is going to be a quite complicated experiment. A lot of the strain measurements and stress measurements, it's hard to measure stress. You can measure strain, but it's hard to measure stress in the reservoir, to get an actual number of the stress. There are some experiments that are going to happen at Ford's that are going to do that. But again, it's a high temperature issue. If you want to do it down there next to it, I mean, there's the borehole methods. There's all the borehole methods you could do that people do in the oil and gas industry. But when you get down to high temperature and you get cementing problems at high temperatures and all these different borehole issues associated with high temperatures, at Ford's, a lot of their fibers failed because of the high temperatures and trying to put them behind casing and bad cement problems at those high temperatures and things of that nature. We didn't get the high temperatures we wanted out at Ford's, but fortunately, the Stefan's group did a great job in eking everything out with the temperature range they had. About 175, correct me if I'm wrong, is probably where they cut off at the high temperatures. And thus why DOE wants to go higher temperatures, and it's necessary, to get closer to the action. That's hopefully will be happening.
I'll just say a little bit. So AFL says they now have a 500 degrees C fiber optic. It actually does have gold plating, so it's pretty expensive. And it hasn't been deployed to a well. They're looking for some place to deploy it, and so we've been talking to them. I think, that to me, the improvement in fiber optic monitoring is the biggest story for both in the oil and gas industry and the geothermal industry. And I think Fervo's demonstration of it was great, but they had their problems as well. And it's kind of a high risk, high cost, but high reward sort of thing to add to your project. I found it more valuable for the DAS than the DSS. I'm not sure that the strain monitoring helps so much with induced seismicity, but maybe that's an area for further research to try to understand how that can help with induced seismicity risk.
Yeah, I think we have time for one more question, and then we'll wrap it up.
Yes. So the other question is from Duan Benshaw, and he's asking, what are hypotheses for mechanisms of delayed seismicity? For example, a significant one after shutting in EGS.
I think did we address this one?
Yeah, we kind of addressed that one.
Okay.
Yeah.
So the other question is from Alexandros Savadis, and his question is from Trenton. In your mitigation plan that you have, stop the injection when PGA greater than 3% G, distance less than 3 kilometers. This is a very small value to have damage to infrastructure. Do you have any ideas about it, Trenton?
I don't think we will be able to change that. I mean, there were surveys of buildings, cabins that said you'd start to get cosmetic damage at those very low levels. And also people could feel it. So I think the standard for accelerations, probably we can't up that much. I'm just glad that we've got a standard on PGA and not magnitude, and I think that's where I don't know where we are on that, but I think 10 years ago we were saying, why are we using magnitude for these triggers? Why aren't we using acceleration, what people feel peak ground acceleration? But it seems like we're still kind of stuck on magnitude. But I don't think we can change that 3% necessarily because of the.
No, that's the tack we're taking into best practices too. I mean, and it's a wide range of ground motions. So we have ground motion experts involved with writing the best practices. It's you go depending on where you are, of course, and what your assets are. It's going to change for every site.
Yeah, but I'm sorry. Thanks for your replies, Trenton and Ernie. But I mean, if it is based on the site, then you cannot make it put it on a guideline. You have to make sure that there are some observed data that you can use as a threshold in that case.
Right. We were working at one site where they said the first time we feel an earthquake, just feel an earthquake, you guys are done. That was their standard.
Yeah. Pretty extreme though.
Yeah.
Great. Thank you all very much. We are 3 minutes past the hour, and you know, if the panel is agreeable to stick around offline to continue the discussion, that would be great. You know, depends on you. But the topic obviously is very interesting, with DOE intending to double the geothermal power generation by 2035. There would be many more geothermal projects, and with that, obviously, the issue of induced seismicity will continue to be with us, and hopefully the investment will have a major impact on technology development for monitoring, data acquisition, and modeling, obviously, because that seems to be also a component that is hindering the actual real-time mitigation processes. So with that, I'd like to thank all of our panelists for their time and sharing their insights with us, and hope to see you all in the near future in an induced seismicity workshop or panel discussion or another ARMA webinar. Have a good week.
Thanks a lot.
Thank you.
You.
Thank
Bye-bye.
you, everyone.
Bye.
So the formal part of the webinar is over. So if you have any direct questions from the panelists, and if they are available for this informal part, you can proceed with your question.
Yeah, it's kind of informal. If anybody wants to raise a point or pose a question or share some opinion or insight, that would be very welcome.
I put one in the chat. I saw a paper recently that suggested that in the UK, surveys of local people, they're more tolerant of small, non-damaging earthquakes from geothermal than from oil and gas. Any comments?
That's good. That's good.
Yeah,
That's good, yeah.
exactly.
Yeah, I don't know who.
So the geysers is an example, right? Maybe Ernie, can you maybe discuss that a little bit more? I mean,
What
there's
they do at the geysers?
Yeah.
Yeah, they don't have any. Their traffic light system is when people start complaining, and they do. They reach out to the community. They increase community outreach. They also have insurance. They also, the geysers, the people who own the geysers, Calpine now. Calpine was recently acquired by a venture capital group, and they're much more tolerant of research than just the operational guys. Same people working up there, but when Trenton was up there with Altarock, you know, they were drilling in the southeast geysers, and they had a heck of a problem. They had stories in the New York Times. I mean, Trenton, you recognize that. I mean, you remember that. And this guy from the New York Times kept calling me up and says, "Well, what are those guys doing up there? What are they hiding? What are they? We're not hiding anything." It's just a difficult situation up there in drilling, and they were afraid, you know, of God knows what. Pretty soon, Dianne Feinstein, which is the senior senator from California, was calling up my boss, Steve Chu, and saying, "You guys get back here and explain how are you guys going to handle this?" And she was very concerned about any type of activity that created seismicity in California, be it oil and gas, be it carbon sequestration, you name it. And so now the Calpine guys have done a great job in terms of satisfying the community. They build a community center, they donate to the community. you know, things, I don't know what they do, but they donate money, you know. And so that's their traffic lights. So, and they do have a quite extensive plan in place for how they inject, where they inject, and how much they should inject at what rates. And so they've already worked it out pretty much, you know. It's an unusual place, you know, it's a huge field, and it's hopefully go on for a long time. So
Ernie, you know, it was pretty dysfunctional back in 2008 and 9 when we were there at Alta Rock, and at that point, you know, Calpine was not cooperating at all, and they were, but to me the really interesting thing, and I don't know if it would be the same now, but is EGS triggered that whole debate, but you know, the operations ongoing that have been ongoing and still are is what was creating all the seismicity. We never got to do an EGS event, create an EGS event at Alta Rock.
right, yeah.
Later on, the Northwest Geysers project at Calpine, they did inject, but that's always been something that is interesting to me, that EGS creates this issue, but conventional geothermal doesn't, right? And I don't know if there's still that bifurcation or not, I guess. And the geysers is the classic place to, you know, observe that, I think.
Right.
Are there examples of that in Europe where people are not, I mean, the UK example was mentioned, but anywhere else in France that people perhaps are more accustomed now to the background level of activity?
What I can comment on this is that I try to point out the difference between the Soul-sous-Forêt context, which is rural and with a long history of underground exploitation, including oil and gas exploitation, and compared to the Strasbourg case where there is only geothermal exploitation. And it is very true that the perception and the feedback from the people to induce seismicity is sort of different. To the north, so in the Soul-sous-Forêt area, it was some felt event, and the reaction was, but it was not too serious. And the people basically didn't complain too much. So it goes a little bit along this line, and our social science colleague, they really say that this experience of undergrad usage is important in the perception and the acceptance of the project. Yeah. But this has to be balanced by some reality that the events in Strasbourg, so sort of only related to geothermal and with a strong reaction, were quite larger and induced real damages to the houses and to the buildings. So then, of course, the impact on the population was much stronger. So I don't know how to take this comment. I mean, it should be according to the impact, of course. Yeah. Also, that's one thing. But in general, I would say that we see really that the kind of strategy is that the project should avoid any felt earthquake, not any damaging, but any felt earthquake. That's where is actually the limit. So for us here in the Graben, it's about magnitude 2. So as soon as it reached that limit, then the problems are getting very different. Yeah. So that's maybe one part of the comment. Another, which is a follow-up of something it was discussed just before, is about this need of getting very high quality data on very small event, which is really for the management of the project. Is who is supposed to have access to those data? Is it just the industrial operator that should look at that, or to have access to that, or should it be public data? And for the uptake, it's very important because of course you have an insight or a view on the project that is very different according to that. And it's a very fundamental question because it is asking or posing the problem of who is deciding on those projects. And we see that the operators, they are very against such a development, and because it's very much related to the assets of their project, but it's very needed for the public acceptance. So how and who is going to sort of deal with that and decide about who is going to share what is very it's a very open question for the moment, I think, at least for us.
Yeah, and it seems to me that also the real-time kind of maybe capability is still maybe not where it should really be. I mean, even the Forge project, I mean, to be able to kind of forecast, you have to understand where the structures are, and then to know where the structures are, we need to know, where the events are taking place, and so on, and getting a sufficient number of events processed. It just takes a long time. At least, current practice seems to be that way. I don't know how we can fix that. And it may be that it's just just the size of the project that is dictating that. But
yeah, I think this is a question. I mean, it's true that as a scientist, the more you have, the earlier you have, and the faster you have information to the project, this looks better. But it's not so trivial at all. I agree with you. There are quite some questions, and also, for instance, from Strasbourg case is an example for that. It's real-time monitoring is one thing, but operators were able to have many operations in a short time because they had a rig on site, a dedicated rig, which is very unique for a geothermal project, at least in Europe. And this was increasing the time scale, or making the process very fast, and with very little time to take some rest in a way, or some time for analyzing and understanding deeply what was happening. And I think that was very against the project, actually, altogether. In one sense, it was a progress because it was much more feasible, much more kind of easy to do many tests and so on. But it's created a big pressure on the operators, in the sense that it was producing so much data and so much new issues so fast that it was a problem to handle them. Yeah.
There was an interesting parallel issue in Oklahoma where, when the oil companies put together a really substantial array that they moved around to wherever the drilling was going on, we sought to, at the Oklahoma Geological Survey, sought to get the data in real time, and they were very wary of doing that. They would send it to us a month later, but of course that meant going back and reanalyzing a whole month worth of earthquakes.
Yeah,
and there weren't enough staff. So it's a real challenge to say, we understand you want to keep this quiet so that you can actually act quickly, instantaneously. We're not necessarily trying to be your cop with that data. We're trying to make sure that our catalog best represents what's going on. The other interesting thing was the number of studies that were beginning to apply some of these machine learning tools and other tools like that to reanalyze earthquakes and get really excellent definition of some quite small faults that were active in that area.
Okay.
Yeah.
The new catalogs, new catalogs have 300,000 events in Oklahoma and southern Kansas, and thousands of faults light up.
Yeah.
So what's the protocol now in Oklahoma? What do they have to do? Anybody who's injecting water, or whatever, what do they have to do? Do you have regulations? How are they regulated?
Jeremy,
4 years ago, they were having to, anybody injecting into the Arbuckle had to report daily results every week in that earthquake area. So you had the injection data pretty firmly. And they put a stoplight procedure in. Once we started seeing some of the frac-related earthquakes, which came on, I think starting in 2017 or 18, they were getting in touch with us, and they put that new array in place. And And, you know, but there was a stoplight procedure, and then it got refined too. I'm not sure what the current status of that stoplight procedure from the Oil and Gas Conservation Commission. They were in charge of that, and they put a lot of new tools in place to try and to enable them to see what was going on with respect to injection and earthquakes.
Yeah, I don't think much has changed since those days. It's same process.
Well, for hydraulic fracturing, since 2016, you also have to report the location, the depth, the volumes. I think 24 hours before you start, they call them not frac notices, something like that.
Right. Yeah. I forgot about that piece.
Great. So any other points of interest, questions, insights? If not, we can just end the informal portion of the meeting and go about our Friday.
Okay.
And thank you.
Thank you, everyone.
Okay, thank you very
Thank
much.
you.
Have a good
Bye-bye.
one.
Great
Bye-bye.
panel. Thank you, everyone. Have a great weekend.
Bye-bye.
Thanks.
Bye.